Well, good morning. It's 11:33, 3 minutes late for the start of linear algebra class. But unfortunately, I'm the only one in the room. Ha! We just got a good deal.
Every time I try to come to class, something's off.
What's that?
It's always on Tuesdays and Thursdays.
All right. We got you here. That's good. All right. I was just saying that I was going to get started, but you walked in, so that's good. Go from current slide. Let me turn on the projector. I usually don't turn it on if there's students in the room. There are maybe a few announcements that you may or may not need to know. First, I'm not going to be on campus tomorrow. I've got to be out of town tomorrow, so I will not be on the Birmingham campus tomorrow during my normal office hours, 8 to 12. And let's see, there's some meeting called, but I think they either got the date or the day wrong. I think they said Monday the 13th of September. Well, the 13th of September is on a Friday, so I don't know if it's Monday or Friday of next week. I may not be here either. I just don't know. There's a meeting at Shelton State that we're supposed to go to. But I'll try to find out more about that as it gets closer. All right. I don't know of anything else. Any questions, anything from what we've done so far?
I think it's on the 16th of October. Will you be at the Phi Theta ceremony?
I've got classes, so I know that another student told me he was going to be there too, and he told me this morning. So, no, I don't think. What time is it?
1 o'clock.
1 o'clock. Yeah, I have a class at 1. It actually starts at, well, it starts at 1:15. So, yeah, I can't be there at it because it's a big class. I know not all the students are going to be there, so I'll need to
I have to be there.
Right.
They open the invitation to come. I'm thinking about I'm not going to join it, so but I'll be there Thursday.
Okay.
So you want to see me in class.
Okay. Well, congratulations on
thank you.
being selected.
Thank you.
And
Is it the Birmingham campus?
I believe it is. That's usually where it is. And I believe probably in the ACAT theater, but I'm not certain on that either. But anyway. All right. Any other questions or issues?
No, sir. We left off. We're about to wrap it up 1.2.
Yeah. We're in 1.2, just the last page of 1.2 before the exercises. So that's on page 21. Chapter 1, of course, is systems of linear equations, and 1.2 is Gaussian elimination and Gauss-Jordan elimination. So we've mentioned this earlier. In fact, in the last discovery, we ran into this. It's a type of linear equations that are called either homogeneous or homogeneous. I don't know which way they prefer the pronunciation. Maybe they don't care, but it's one of the two. But systems of linear equations in which each of the constant terms is 0, is called homogeneous or homogeneous. Okay? So a homogeneous system of m equations with n variables would be like this. Let me get my pen set up. All right. A sub 1, 1, x sub 1, plus a sub 1, 2, x sub 2, plus a sub 1, 3, x sub 3, plus dot, 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 plus, and since you had n variables, it goes to a sub 1, n, x sub n is equal to 0, rather than a b1 or whatever we have been calling it before. And then similarly, a sub 2, 1, x sub 1, plus a sub 2, 2, x sub 2, plus a sub 3, 2, 3, x sub 3, plus dot, 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 up to and including a sub 2, n, x sub n. That's also equal to 0. and then a sub 3, 1, x sub 1 plus a sub 3, 2, x sub 2 plus a sub 3, 3, x sub 3 plus dot, dot, dot plus a sub 3 n x sub n. That one's equal to 0. And then we dot on down till we get to the a sub m. We have m equations, n variables, okay, plus a sub m2, x sub 2, plus a sub m3, x sub 3, plus dot, 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 plus a sub m n x sub n. That's also equal to 0. So you got dot dots everywhere. Everywhere's a dot dot, and there's a dot dot, and there. All the equals are 0. That's a homogeneous or homogeneous equation. Now, a homogeneous system of 3 equations and 3 variables, x1, x2, x3, must have, okay, I'm sorry, let me, before we get there. A homogeneous system must have, will have at least one solution always. This will not be one of those that has no solutions. Can't possibly, because if you choose x1 equals 0, x2 equals 0, x3 equals 0, x4, all the way up to x sub n equal to 0, if all the variables are 0, then the answer's got to be 0. So that would fit, that fits every one of those, okay? So you will have a solution. Now that's called the trivial, or sometimes called the obvious solution, okay? If all the variables have the value 0, that's called the trivial solution, okay? And the obvious solution. So let's go to example 9, and just to keep from running out of space, I'll erase this, okay? Okay. X sub 1 minus x sub 2 plus 3x sub 3 is equal to 0. 2x sub 1 plus x sub 2 plus x sub 3, no, 3x sub 3 is equal to 0. Okay? Says solve that system. Okay? How would you propose we solve it?
First, arrange the matrix brackets.
Okay. We'll do our matrix representation. And what would that be?
It's going to be 1.
1.
Negative 1.
-1.
Positive 3.
3. And 0. Okay, next row.
2. Positive 1.
Uh-huh.
And positive 3.
Second.
0.
3 and 0. Perfect. Okay. Now, how would we proceed to solve this? Okay. Once you get your matrix done, then what you look for first is a 1. The first non-zero entry in the first row, you want to be a 1. Hey, we got it already. We don't have to do a thing to make it. Then what we want is 0 below. So how do we make that 2 become a 0?
Use, I guess, elimination.
Yeah, okay. And how we're doing that, not thinking in terms of equations, which elimination by addition, but exactly that concept. Multiply the first row. You're using the first row because it's leading 1. Okay? Yeah. So how would you do it? Okay, now -2 times row 1
-2 times.
plus row 2 is the new row 2. Okay? Yeah, if you multiply the leading 1 by the opposite of what you're trying to eliminate, that'd be a -2, then add them together, it goes to 0, doesn't it? That's the adding a multiple of one row to another row. That's one of the 3 legal operations we can do. So our first row stays just like it is, 1 minus 1, 3, 0. The new second row is now what? 0. 3. Positive 3, you got it. Negative 3, you got it. 0. Oh, these homogeneous ones are really easy to do. That last column is always going to be a 0. All right, what's the next thing we want to happen? Just a quick do. First thing we wanted was first non-zero entry here to be a 1. We got it. We want 0 below it. We've got that now. So next we go to the second row. The first non-zero entry we want to be a
row 2.
Huh?
Row 2 by row 2.
Okay.
Row 2 by row 2.
What do you mean by that?
You multiply. You're gonna multiply both rows.
By what?
Multiply both rows
By what?
by each one. No, I see what I'm saying. I don't make any sense.
Yeah. Okay. Here are the 3 legal operations. Exchanging 2 rows, we don't want to do that. Multiplying one row by a constant, okay, not 0, okay, never multiply by 0, okay, or divide by 0, okay, or adding a multiple of one row to another row. That's what we did here. So what we want here, we want this to be a what? First non-zero entry, we want to be a 1. So how do we make the 3 become a 1?
You're going to use.
Remember the 3 things. Exchanging 2 rows, that won't make it become a 1. Okay? Or it'll mess it up totally. Secondly, multiplying one row by a non-zero number. Will that work?
Yes, sir.
What non-zero number can you multiply by?
It's going to be 2 in this case.
Second, you want that to become a 1. How do you get 3 to become a 1? By multiplying by something. Or hint, divide by something other than 0.
3?
Yes, if you divide by 3, which is same as multiplying by 1/3. Okay, so what we'll do is row 2 divided by 3 is the new row 2. All right, so now what we've got is 1 minus 1, 3, 0. 0, you tell me what to put next. 1, negative 1,
and
0. Good deal. Now, we've got it in row echelon form. Probably better to go on and get it in reduced row echelon form for Gauss-Jordan elimination. So what we want is first non-zero entry in the row 1 to be a 1. We had it. Okay? 0's below it. We got it. Next, the first non-zero entry in row 2 to be a 1. Now we have it. Now what we want is the entry above it to become a 0. How do we make that become a 0? How do we get this minus 1 to be a 0? Using the bottom row.
We're going to use 1.
Yes. Not multiply. Huh? No, not dividing. Add it. Add the multiple of one row to another row. That was the third rule. Third thing you can do. If you add row 2 to row 1, that negative 1 becomes a 0. So we're going to row 2 plus row 1 is the new row 1. Okay? So let's write down row 2 first. 0, 1, minus 1, 0. We're using that one, so we're not going to change it. What's the new row 1? 1, 0, 2, 0. Perfect. Okay, now we've got as far as we can in reduced row echelon form. We got a 1 here, 0 below it, 1 there, 0 above it. We can't do a thing with that third variable, our x of 3. So what do we do with that? A little louder. Okay, and what's that free variable, if you want to call it that? That's fine. You want to pick one? T, is that what you said? That's what they love to use, T. Now, what does the second row tell you? This represents the coefficient for x2. So this says x2 minus x3, but x3 is T, is equal to 0. Okay? Which means, or implies, that x2 is also equal to T. Okay? What does the first row tell you? x1 plus 2t is equal to 0, which implies that x1 is equal to minus 2t. Right? Yeah, he had a phone call. Okay? Now, our ordered triplet, you don't have to write it this way, I found it a little easier too, is minus 2t, t, t. Okay? Now, sometimes I'll write this way. Okay? Especially since there's no constants to add to it. You can pull the t out and just say t times minus 2, 1, 1. Okay? Any t you want to put there, that'll give you an ordered triplet that should satisfy that first equation. Now, obviously, t equals 0, that'll do it. The trivial solution always works. But if t was equal to, say, 1, that would be a minus 2, 1, 1. Let's see if that works. Minus 2 minus 1 would be minus 3, plus 3 times 1 is 3. That's equal to 0. Minus 4 plus 1 plus 3 plus 4. Minus 4 plus 4 is 0. Yes, that works. Any t you happen to choose. Infinite number of solutions. In fact, you almost knew this had to be the case because you have more variables than you have equations. You know you're going to have an infinite number of solutions because this is homogeneous. If that wasn't homogeneous, you couldn't guarantee. You would suspect it might, but you couldn't guarantee. But since this is homogeneous or homogeneous, yeah, you know that has to, because you know it has to have one solution, the trivial solution. And since it has one, it's going to have an infinite number because you have more variables than unknown. So let's see what they got. x1 equal 2 minus 2t, which we got. x2 equal t and x3 equal t. All right, infinitely many solutions, one of which is a trivial solution. So let me write down theorem 1.1. Since they're not going to do anything with it except to state it here, let me just state it. Okay? Every homogeneous or homogeneous, I don't care, I don't know which way you prefer to call it, homogeneous or homogeneous system of linear equations is consistent. What do we mean by consistent? It has at least one solution. Okay? And if it's a homogeneous system or homogeneous system, the trivial solution is always a solution, so it's got to be consistent. Moreover, okay, if the system has fewer equations then variables, just like we saw before, then it must have infinitely many solutions. My writing is terrible. Okay. And what they say to prove that theorem, use exactly what we did in example 9, but in a general matrix where you don't have any numbers in them, just A1s, A2, A11, A12, yeah, that kind of stuff. All right, it's just what we demonstrated. We didn't prove it, but we demonstrated that. Okay. Good deal. Any questions on 1.2? Homework exercises here would include any of the odds 1 through 5. They're all at calcchat.com. Either 7 or 9, they're at calcchat.com. Any of the odds 11 through 17, all at calcchat. 19 through 23, they're all at calcchat. 25 to 29, no, I'm sorry, 25 to 37, they're all at calcchat. 39 should be at calcchat. Now they suggest there you need to use a software program or graphing utility to solve it. See what you can do without that, but if you get too bogged down, just forget it unless you happen to have a graphing utility. Either 41 or 43, they should be at calcchat. 45 should be at calcchat. 47 should be at calcchat, and 49 should be at calcchat. All right. 51 should be at calcchat. 53 should be at calcchat. 55 is a writing problem. I would say think through that one. True false. 57 is a true false. So take a look at that one. 59 is writing, so you can read through that and think through it. Now, uh, 61, I was trying to see if that's introducing anything new. I don't think so, so you should be able to do 61. It should be at calcchat. Now, 62 is a little bit of a different, 63 is a little bit of a different type of problem. Their coefficients there are a number called lambda minus 2, okay, for 63. And you can certainly play around with that and deal with that. It should be at calcchat, so if you need some help with it, that should be there. 65 is another writing problem, so you can read through that if you'd like, and 67 is also a writing problem, so you can read through that. So now we're moving on to 1.3, which is applications of systems, of linear systems. And we're not going to do all of these, but we're going to do a few, okay? And perhaps I'd forgotten how this, because we're not going to do them all, we get through it pretty quickly. I don't have your test, I have your test ready, I just don't have it run off, but I can run down and make copies real quickly if we get far enough along on this, and we might. Let me get my watch out so I can keep track of time, and if it looks like we do, I may go on and give you the test, even if we don't quite finish it. That way you can be working on it. You have an extra weekend to work on it, because you always have at least a week, and this will give you a weekend plus a week if we don't, even if we don't finish it. Okay, the first application of systems linear equations is what they call polynomial curve fitting. Okay, there was nothing in the course description that indicated we needed to do this. So what I think I'll let you do is read through this on your own. It's a pretty let's see how to phrase it. pretty straightforward type thing, only it can get bogged down in complexity just if you have too many points. But basically, I'll tell you this. If you are given, like that first example, or figure 1.4, if they give you 1, 2, 3, 4, 5, 6 points, a 6-degree polynomial is guaranteed to match those. Okay? If you're given 3 points, a 5th-degree polynomial is guaranteed to match it because it's n minus 1. Figure 1.5 shows 3 points, so a second-order polynomial is guaranteed to match that. The reason it's 3 constants, well, in the first one, 6 constants, but you see, you always start with a constant, a0, a1 times x, a2 times x squared, and a3 times x cubed. So you see, third-degree polynomial would have 4 constants. So 4 constants will fit a, if you have those 4 points, you can make it fit. Exactly. Okay? So I won't get into, well, it just takes so long to do these. I have done some of these in the past. I want to bring your attention to example 3 on page 26. What if you had something like this? Your points are years and values. 2006 was 3, 2007 was 5, 2008 was 1, 2009 was 4, 2010 was 10. I don't know what they're measuring there, but maybe this is the number of hostile takeovers or anything such as that. Well, to use 2006, 2007, 2008, 2009, 2010, that's just a huge numbers. So what you do sometimes is just, my first reaction would just be use 6, 3, 7, 5, 8, 1, 9, 4, and 10, 10. Okay? That would be one way to shorten that, use smaller numbers. And then at the end, go back and put in the 2000 and blah. Okay. What they say, because the x values are so large, they pick the middle value, 2008. You see you had 6, 7, 8, 9, and 10. Pick the middle value, 2008, and then subtract which value you're going to next from that. So the first would be 6 minus 8, that would be minus 2. 7 minus 8 would be minus 1. 8 minus 8 is 0. 9 minus 8 is 1. And 10 minus 8 is 2. Okay. Goodness, my head's stopping up. Now, so there's a variety of ways you can do that. An example they give there, example 4, is the mean distance of a planet from the sun and relating that to its period. Okay? And a 4-parameter system will work, which is a third-degree polynomial, would fit it perfectly, but you can do this with just a second-degree polynomial. That still fits it pretty closely. And you can read through and see how they do that. It's, again, just a little tedious, but it's really not too bad. Now, what their mean distances are in astronomical units, if you're not familiar with those. So, whereas Earth's astronomical unit is 1, because that's how you define an astronomical unit is Earth distance, the mean Earth distance from the sun. So that's going to be a 1. So Mercury's closer, Venus is closer to, but not as close, and Mars is about 50% further away. Okay, 52.4% in fact. All right. So again, you can fit the data like that, and you see they still fit remarkably close. Okay. Now, that was just a 3-parameter system, second-degree polynomial. All right. Actually, Kepler's laws is, I think it's his third law of planetary motion, breaks this down, and they actually do a I was going to, it looks like this one, but what they did basically is called a log transform, and this is where Kepler's third law comes from. See, you got pretty close using a second-degree polynomial. If you really want to get close, use a log transform, and that is incredibly close. They just line up almost perfectly there. All right, those are examples, polynomial fitting with a log transform thrown in at the end. That's one application of systems of linear equations. This next one, though, is network analysis. And because I'm guessing, are both of you pre-engineering? Oh, you're not. What are you?
Physics.
Physics. Oh, okay. But you're pre-engineering, right? Okay. Will you? Yeah, if you're physics, you're going to be taking electricity and magnetism out the ears probably, so you're going to have lots of this. This pertains directly to, now it's not just electrical networks, it's any kind of a network, but it really pertains really strongly to electrical networks. So you'll see this over and over, okay? The first network they outline here, though, is not necessarily an electrical network, but it is a network of types. Now, let me give the same example, because not all of you have books, so let me show this. Here is a very simple network, okay? You have 25 coming in to a node, okay? That's what I like to call those. Leaving that, you have 2 paths, you might say. One could be x1 and one could be x2. Okay? Now, it's pretty obvious to me, if 25 are coming in and x1 and x2 are going out, there's no sink here, there's no source here. There's nowhere you can store the things. So this says that x1 plus y, x1 plus x2 is equal to 25. Okay? What comes into a node has to leave the node. Or, like, what left a node has to come into the node. So that's one of the rules of network analysis. You can't just have a source or a sink there. X plus 5 must, x1 plus y1, I can't talk. x1 plus x2 is equal to 25. So let's move on to example 5, which is a little more complicated of a network, but it's still not too bad. What we have here, a node here we're going to call node 1, a node up here they're going to call node 2, one in the middle here we're going to call node 3, one at this corner node 4, and this corner node 5. Okay? And they give you some pieces of information. 1 and 2 are connected, and it goes from 2 to 1. 1 and 4 are connected, and it goes from 1 to 4. Okay. 4 and 5 are connected, and it goes from 4 to 5. 2 and 5 are connected, and it goes from 5 to 2. 1 and 3 are connected, and it goes from 1 to 3. 2 and 3 are connected, and it goes from 2 to 3. 3 and 4 are connected, but it goes from 3 to 4. And 3 and 5 are connected, and it goes from 3 to 5. Okay. Now they also give us some values for some of these and unknowns for others. Up here from 2 to 1, we know that 20 units pass that way, going from 2 to 1. From 1 to 4, we just know that x1 units goes there. From 1 to 3 is going to be x2 units. From 2 to 3 is x3 units. From 3 to 4 is 10 units. Three to 5 is 10 units. 3 to 5 is 10 units. I'm having trouble talking. And 4 to 5 is x5 units. I think I'm missing one. 5 to 2 is x4. Okay, I think I've got them all labeled now. Okay. Now, what your system of equations are basically what's happening at the nodes. Okay? So let's pick node 1 first. What we see happening at node 1 is you got 20 coming in and x1 and x2 leaving. So from how we just described that, this says that x1 plus x2 is equal to 20. Okay? Because whatever goes out has to be coming in. Right? You don't have a sink or a source there. Okay, let's go to node 2. Node 2 has 20 leaving, x3 leaving, and x4 coming in. So, 2 are leaving, 1's coming in. There's 2 ways you could write that. How would you like to write it? Okay, I can't quite hear, sorry.
x4 minus x3.
Okay.
Well, negative x2 plus x4.
Okay. Now, I'm pretty convinced what you said is right, but since I can't hear well, I'm going to just take the arrows and go with them. And I'm going to say this. 20 plus x3, that's what's leaving, has to equal x4. Agreed with that? Okay. Now let's flip things around a little bit and say, let's subtract 20 from both sides and subtract x4 from both sides. That would give us x3 minus x4 is equal to minus 20. Now, did you say it the other way? Yeah. Okay. Perfectly fine. Either way is correct. Either way is correct. x4 minus x3 is positive 20. Perfectly fine. You can do it that way. Either way is correct. They're both correct statements. Okay? Now let's go to node 3. You got 2 coming in and 2 going out. So it looks like to me that x2 plus x3 is equal to 20. Because you got 2 going out, 10 and 10 is 20. Make sense? And just for fun, I'm going to put a plus here to remind me that is a positive x3 there. The way you did it was probably a minus x3 plus x4 is equal to positive 20. It's fine. Let's go to node 4 down here. 2 coming in, 1 going out. Okay? Now I'm going to write it just like that. x1 plus 10 is equal to x of 5. And again, it doesn't matter how you do. In fact, I kind of like your method on this better. Let's say minus x1 plus x5 is equal to 10. What I've done is subtract an x1 from both sides, and this side has nothing. This side has 10 is equal to x5 minus 1, so that's the same thing here. So I'm going to put minus x1, ooh, I didn't leave enough room, plus x5 is equal to 10. Okay, that's node 4. At node 5, you got 2 coming in, 1 going out, so just to start off with, I'd say x5 plus 10 is equal to x4. Okay. And not for any particular reason, but, well, I sort of do. I think I would subtract x5 from both sides. And that gives me x4 minus x5 is equal to 10. Now, again, these are not unique. You can write them as long as they're correct any way that you want to arrange the signs. Because if you notice, the way you did this one, you had the opposite signs here, and that just is multiplying this equation by minus 1. Minus x3 plus x4 is equal to 20. So that's a legal thing to do, multiplying by a non-zero number. Okay? So this is our system of equations. Now I'm going to erase these that I did on my scratch work down here because I don't have enough room to keep them. But I hope I've got them right. Now this may or may not look like the way the book did it. It doesn't matter. Anyway, as long as you're doing what you're doing is correct. Okay. Now, what would be your next step to solve that system of equations?
First set up the matrix bracket.
Okay, and what would that matrix be? 1, 1, 0, 0, 0, 20. Next one? 0, 0, 1, negative 20. Okay? Next one? 0, 1, 1, 0, 0. That would be positive 20. Okay? I'm having trouble keeping my things lined up. Okay? Next one? I put a minus 1. Okay.
Is it positive or negative?
I've got a negative here.
Okay, yeah, that's right. Yeah, you're right.
Okay.
You're right. 0,
0,
0,
0,
0,
0,
negative 1.
that's a plus.
Oh, positive 5.
No, it's not 5. 1. Just 1. And that's equal to 10. And then the final, I didn't Get my line long enough here. Finally, we get a 0,
0, 0, and 1.
Okay.
Positive.
1,
1, 10.
minus 1, 10. Right? Agreed?
Yes, sir.
Okay. Now, as far as leading ones, it seems like we've got plenty of those. Okay. But some of them may get screwed up. But the first one is just where we want it. We want that first one to be a 1. Now we want zeros below it. Okay? We got a 0 there, we got a 0 there, we got a 0 there. This needs to become a 0. How will that happen? No dividing. Add these two rows together. Right? Now remember, here are the 3 steps you can do. You can exchange 2 rows anytime you want to. You can multiply by a non-zero, and that includes dividing by a non-zero constant anytime you want to, the entire row. Or you can add a multiple of one row to another row. That's what we're doing. We're adding 1 times this to that. That'll make a 0 here. Right. It's going to mess up some of the others, but it's going to do that. So down here we're going to do row 1 plus row 4 is the new row 4. Okay. Now this bad news here is you got a lot of writing to do. Okay. You got to write these things over and over and over again. So this is going to be 1, 1, 0, 0, 0, 20. This one you don't want to change either. In fact, let's go on and do this if it's all right. Since I see that's going to be a 0, that's going to be a 1, let's exchange these 2 rows at the same time. Exchange row 2, exchange with row 3. And you can do that anytime you want to. So let's do that so we have that one where we want it. So we have 0, 1, 1, 0, 0, 20. And exchange that one 0, 0, 1, minus 1, 0, minus 20. Okay? Now let's operate on row 4 like we said. 1 plus minus 1 is 0. I can't get the pen to write. Okay. Then add 1 plus 0, you get 1. 0 plus 0, you get 0. 0 plus, well, I already did that one. 0 plus 0, you get 0. 0 plus 1, you get 1. And 20 plus 10, you get 30. Okay. And the last row, perfectly fine as is. So 0, 0, 0, 1, minus 1, 10. Okay. All right. Stop and assess. What do we want and what do we have? We have a 1 here, 0 is below. Good. We also have the 1 here, just like we want it, but we need zeros here and there. So let's do this one first. What do we do to make that 1 become a 0? Using this 1 with the leading 1. Minus this plus this gives you
-1.
Yeah. Negate this, so minus row 2 plus row 1 becomes the new row 1. All right. So let's write it down. Minus row 2 plus row 1 is the new row 1. Okay? So we're using row 2, that's our leading 1, so let's write that down. 0, 1, 1, 0, 0, 20. Okay? We just changed the top row. What will it be now? Minus row 2 plus row 1. minus row 2, which is minus 0, plus 1 is 1. 0. Minus row 2, that's minus 1, plus 0 is minus 1 plus 0.
Oh, 1.
Negative 1, okay. Then the next one is 0. Next one is 0. Minus 0 plus 0 is 0, right? But that last one, what does that give us? Minus 20 plus 20 is?
0.
0. Oh my. All right. Now, the third row is just like we want it. Leave that alone. 0, 0, 1, minus 1, 0, minus 20. Okay. The fourth row. Okay. The fourth row, we want that to become a 0. So how, using our leading one here, how do we get that to become a 0? Negative row 2 plus row 4 is the new row 4. So negative 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 1 plus 0 is
1.
Negative 1. Negative 1 plus 0 is negative 1, right? Okay. Negative 0 plus 0 is 0. Negative 0 plus 1 is positive 1. Perfect. And negative, I'm on the wrong row, am I not?
Yeah.
I'm sorry. Okay, let's start over. Negative 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 1 plus 0 is negative 1. Okay? Negative 0 plus 0 is 0. Negative 0 plus 1 is 1. No, I'm on the right one. And negative 20 plus 30 is negative 20 plus 30 is positive 10. Perfect. All right, now we look at the bottom row. It's already a 0 underneath that, so you just write it down. 0, 0, 0, 1, minus 1, 10. All right. All right, let's go back and do a quick review of what we've got and what we want. We've got a 1 here and 0 is below it. Good. 1 here, 0 is above and below it. Great. Okay. We got a 1 here, just like we want, but we need to change that to a 0, that to a 0, this to 0. That one's going to be fine. Okay. So let's start with the top one. Okay. I'm hoping that's a minus 1 and not just a dot on the page. Does anyone recall? I think it is a minus 1. Yeah. Okay, so that's a minus 1. So how, using this row, that's our leading one, how are we going to get that one to become a 0? And frankly, I don't think I'm going to have room at the bottom to fit all this in. So let me erase this, and I'll also erase, whoops, this up here. I hate to do it because that's my original equations, but I just don't have room. So hopefully I won't need those again. Hopefully I haven't made a dumb mistake. I should have really checked my work before we started doing this. But it's a little late now. Okay. Okay. All right. Yeah, I think we're okay. So, we're going to use row 3 to change that to a 0. So how are we going to do that?
Add row 1.
Row 3 plus row 1 is the new row 1. Perfect. So add them. 0 plus 1 is 1. 0 plus 0 is 1 plus minus 1 is 1 plus minus 1 is 0. Minus 1 plus 0 is minus 1 is minus 1. Minus 1 plus 0 is minus 1. 0 plus 0 is 0. And minus 20 plus 0 is negative 20. All right. Now, we're using row 3, so let's fill that in. 0, 0, 1, minus 1, 0, minus 20. So we don't forget and try to change that. That's the one we're using. All right. Now we need that to be a 0, too, using this row here. So what are we going to have to do? Okay, no, let's not do that. If you do that, then you're going to mess this up.
Okay, yeah.
Okay? Using this leading 1, how do we get that to become a 0?
Right.
Yes. Minus row 3 plus row 2. That will do it. Minus row 3 plus row 2 is the new row 2. You see, we're always using that third row. That's the one I always lead off with. When I'm using the second row, lead off with that. Using the first row, lead off with that. Okay? So, all right. So, here we're going to do what we said. Minus row 3 plus row 2. So, minus 0 plus 0 is 0. Minus 0 plus 1 is 1. Minus 1 plus 1 is 0. Minus a minus 1 plus 0 is?
Minus 1 plus 0?
Minus a minus 1.
1.
Plus 1. Got it. Minus 0 plus 1 plus 0 is? 0. And minus a minus 20.
0.
Now, minus a minus 20 is a plus 20. Yeah, that's going to be 40. Okay. All right, so now we've got row 1, 2, and 3 taken care of. Let's row 4. We need that minus 1 to become a 0. How can using the row 3 get that to become a 0? Using the leading 1 there to get that to become a 0.
Subtract.
No, just add them together.
Oh.
Right? 1 minus 1 is 0.
Oh, okay, yeah.
Yeah. Add those two numbers together. Okay? So that would be row 3. Always start with the one you're using. Plus row 4 is the new row 4. Okay? So that will be 0 plus 0 is 0. 0 plus 0 is 1 minus 1 is 0. Minus 1 plus 0 is negative 1. And 0 plus 1 is 1. And minus 20 plus 10 is negative 10. Is that what you said? Minus 20 plus 10. Right? Okay, be careful with these things. Okay, now we look at row 5. We've already got a 0 there. And that's exactly what we want under that leading 1 is a 0, so we just copy it down. So that will be a 0, 0, 0, 1, minus 1, 10. Okay. Now, at this point, I can see that those two bottom rows are basically saying the same thing, aren't they? Okay? And that's what we want. We have if I did this right, that means if you add these two rows together, that gives you a row of zeros here. So that means this is not a solvable system, and I didn't think that's the case. So I may have made it, nope, they got it too. Yeah, okay. I was beginning to worry a little bit, because we have 5 unknowns, and I thought we were going to have, yeah, we're okay. So what I'm going to do now is just add these two rows together and make that my new row 5, okay? That's going to be the easy thing to do. I know it's not quite in the right order, but it's going to be the easy thing to do. Okay, I'm going to have to cram a little bit. So my first row is 1, 0, 0, minus 1, 0, minus 20. Second row, 0, 1, 0, 1, 0, 40. Third row, 0, 0, 1, minus 1, 0, minus 20. Fourth row, I'm going to leave the fourth row out for right now. Now we're going to add these two rows together, because I always want my rows of zeros to be at the bottom. So I'm just going to add row 4 plus row 5. I know we don't usually do it that way, but it's okay to do it, okay? Because it's a legal move. That would be 0, 0, 0, minus 1 plus 1 is 0, plus 1 minus 1 is 0, and minus 10 plus 10 is 0. That row gives us nothing, literally, okay, nothing, all zeros. Now, I do want to change my fourth row. Now that I've done that, I want to multiply by minus 1. Minus row 4 is the new row 4. I'm going to negate everything. So minus 0 will be 0, minus 0 will be 0, minus 0 will be 0. And see, I want a leading 1 there, a positive 1. That's what we want. So that makes that a plus 1, a minus 1, and a plus 10. See what I did? Just multiply by minus 1. That's a legal move. Okay. So now we've got our matrix in, no we don't, not quite, I skipped. We got a leading 1 here, but we need zeros above it. We got a 0 below it, but we don't have zeros above it. So let's go back and get zeros up there. Okay, now, I'm going to have to erase this matrix here. How are we doing on time? We're running out fast, aren't we? Okay. Let's see if I can do this quickly. I don't do many things quickly. So let's see if we can. This is where I'm going to put my new matrix, so ignore this. Okay. Okay. Now, let's review what we've got and what we want. We got a 1 here, leading 1, zeros below it, a leading 1 here, zeros above and below it, a leading 1 here, zeros above and below it, and a leading 1 here, but not zeros above and below it. We got it below, but not above. So what are we going to have to do using this leading 1, row 4 leading 1, to get that to become a 0? Add them together. Row 4 plus row 1 is your new row 4 plus row 1 is the new row 1. Okay? So, I'm going to write in row 4, 0, 0, 0, 1, minus 1, 10. Going to write in the last row, 0, 0, 0, 0, 0, and 0. Okay? Going to leave those two blank for now and do my new row 1. It's row 4 plus row 1. So 0 plus 1 is 1. 0 plus 0 is
0.
And 0 plus 0 is
0.
And 1 minus 1 is
0.
0. And minus 1 plus 0 is minus 1, and 10 minus 20 is negative 20, negative 10, right? 10 minus 20 is negative 10. Let me clean that up so I don't misread it later. Okay. That's not clean, but it's better. Okay. Now, what we want next is that 1 to become a 0. How are we going to use row 4 to get that 1 to be a 0? How do we use this leading 1 to make that 1 become a 0? Yeah. Minus row 4 plus row 2 is a new row 2. Minus row 4 plus row 2 is a new row 2. So minus 0 plus 0 is 0. Okay? Minus 0 plus 1 is 1. No, minus 0 plus 1. Wait, that's a 0. I had a 0 there, but it disappeared. Okay? That's a 1. Row 4. Okay, I was looking at row 3. Minus 0 plus 0 is 0. Now we finally get to the 1 in question. Minus 1 plus 1 is? Minus 1 plus 1 is? Minus 1 plus 1. 0. Okay. Minus a minus 1, which becomes a plus 1 plus 0 is? No. Minus a minus 1, that becomes a plus 1, plus 0. 1 plus 0 is? 1. Okay. And minus a 10 plus 40 is? 30. Perfect. Okay. Now the last thing we need to do is get that minus 1 to become a 0. How can we do that using the leading 1 there? This is the last one we need to work on. Okay? How do we get that to become a 0 using this leading 1? Add them together. So row 4 plus row 3. Row 4 plus row 3 is the new row 3. Okay? And that's what we're waiting on here. Row 4 plus row 3, that 0 plus 0 is? 0. 0 plus 0 is? 0 plus 1 is? 1. 1 minus 1 is? 0. Minus 1 plus 0 is? Minus 1. And 10 minus 20 is? Minus 10. Perfect. Now we've got as far as we can go. We got a 1 here, 0 is below, 1 here, 0 above and below, 1 here, 0 above and below, 1 here, 0 above and below, all zeros here. We've got it in reduced row echelon form. All our leading 1s have zeros above and below. But we can't do a thing with here, so what do we choose this to represent? And remember, that was our X4. That's where I'm sorry I erased it. No, X5. That was X5.
Yes, sir, that's 5.
Yeah, X5. So what do we assign that? T, the parameter T. We don't have anything we can do that, so we'll say let X5 equal T. Okay? Now what does this equation right here above that tell us? That says this represents X1, X4. This says X4 minus X5, but X5 is T, so minus T is equal to 10. So that says X4 is equal to T plus 10. Right? Just add T to both sides. Right? Okay, let's move up to the next row. And this represents x3, so that's x3 minus x5, but that's t, minus t is equal to minus 10, right? That's what it says. So that tells us that x3 is equal to t minus 10. So x3 is equal to t minus 10. Okay, let's move up to the next row above it, and that's x2 there. I'm running out of room. x2 plus t is 30. So that means x2 is equal to 30 minus t, right? Subtract t from both sides. And then finally we have x1 minus t is equal to minus 10, and that tells us x1 is equal to t minus 10. Okay. Now, t is any real number, so this has infinitely many solutions. This network, you can't just plug anything in, but once you choose that t, then you can go with it. For instance, one solution would be let t equal 0, and your solution would be minus 10, 30, minus 10, 10, and what does that? 0. Okay? Let t equal 0. Okay, you could go and plug and look at that and see if that works. X1 is minus 10, so in other words, 10 going the other direction. X2 was 30. So 10 plus 20 is equal to 30. Yeah, you can go back and everything will fit then. This will have an infinite number of solutions depending on what t you choose. If you wanted to guarantee t is always going to be positive, for instance, then you could just pick a big enough t to make that happen. You know, so whatever. Afraid we are out of time, aren't we? So we didn't get quite finished, okay? And that's where I wanted to get to was electrical networks, okay? So we'll pick up there on page 30 when they talk about Kirchhoff's law. Okay? Now, we haven't done that yet. We'll do that next time. Do you want to go on and get a copy of the test so you can be working on it? Or wait and get it on Tuesday? So either one, I don't care. You game? Okay. Let me see. I might just have 2 copies here. I doubt it. Let me see. Test 1, 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 test 1. Nope. 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 Okay. I don't have any. So let me run down and make 2 copies real quickly. I'll bring them right back up. I'm going to go on and put this on pause. In fact,